In this problem, we are given a block being pushed up a 30-degree incline. We are given the force F and its mass, and we are asked to calculate the magnitude of the acceleration of the block. And we are taking note of our equations, F equals ma, where the acceleration is going to just be force divided by mass. That's how we're going to find the magnitude of the acceleration. All we have to do, well, this is actually going to be our net force in this problem, is we have to find the net force acting on this block. And that means a free body diagram. And so we're going to draw the block as a point. We have force F, which is 90 newtons. We have force of gravity, and we have a normal force. Force of gravity, F sub g, is always equal to mass times gravity. And so in this problem, it's going to be 5 times 9.8. So our gravity force is 49 newtons. The last force we actually have is our normal force, which is a sort of reactive force. And that normal force is actually going to cancel out both of these forces in sort of a normal situation. If this block was stationary, not moving, we would know the net forces are 0, and our normal force sort of needs to cancel everything out. So here, we're actually going to have a little bit of a hard time figuring out what our normal force actually is. So what we want to also take a note of is that there is no friction, and so these are the only 3 forces we have, right? So it's frictionless. So, well, let's take a look at the idea that the normal force is perpendicular to the motion. There's a point here, right? The normal force cancels out perpendicular forces to the incline, but any force that points along the incline actually just sort of gets on by. So we would actually do quite well to reorient our x and y axis. This picture here takes the standard x horizontal and y positive up and down coordinate, but in this problem, we would actually do much better to assume that the incline of the ramp is the x-axis. Because now, if we do so, this is our mass. And the force points down at an angle of 30 degrees. Gravity, let's just move down a little bit. Gravity acts at an angle of 30 degrees. F sub g, F. And our normal force acts just straight up, N. And in this situation, it actually becomes much clearer how we calculate what our normal force is and how we calculate what our acceleration is. Because remember, the direction of the box's movement, we know exactly which direction the box is moving, up the incline. And in this xy coordinate plane, this new one, up the incline just means in the negative x-axis. That's its direction of motion. And if we know we are constrained to only motion in the x-axis, we can say that a sub y equals 0, right? If there is only motion in the x-axis, a sub x is some unknown, right? We don't know what that is. That's what we're trying to find to help us solve this problem. But our y acceleration is 0 because there's no motion in that new y-axis. This is sort of our y and our x here. And remembering that F equals ma, well, if a sub y is 0, then F sub y is 0. Or the net force in the y direction is 0. And so since this object has no motion in the y-axis, we can say that the net force in the y direction is 0. And that leaves us to only evaluate the x direction. And we know the magnitude of F to be 90, and the magnitude of FG to be 45. So let's just try and find the net force in the x direction. Right? And we can find that because we have two forces generating an x component, right? The normal force is only in the y direction, and so it has no x component, but both the force of the push and the force of gravity have x components. Right, so our net force in the x direction is equal to, well, what's this component from the force? Well, we know it's 90, and it's multiplied by either sine or cosine, depending on whether we are looking at our x or our y sort of component. It might be helpful to move to a slightly clearer drawing, where F points down, N points up, FG, G, and F, where they both make 30-degree angles. And we're looking at the x-axis, sort of this component. That's actually opposite this 30-degree angle. And remember, with opposite, that is sine. Sine of 30. So our x component of this force is just going to be the magnitude, the hypotenuse, 90, times sine 30. And this is actually going to be a negative force. And so this all just comes from basic trig and sort of working with vectors. And as you get more comfortable, we usually try and avoid having to draw a triangle for every single vector we evaluate, right? Being able to do this, where we can fit our triangles into the free body diagram, takes up less space and it's a little bit faster, right? And being proficient with this trig is very helpful in this class. Being able to understand this. So it's just practicing until we can be pretty fluent with this. Our next force is the force of gravity, right? And this is a positive x direction, so it's going to be a positive force. And it's the hypotenuse times, well, once again, it's going to be sine 30. Because remember, SOHCAHTOA, sine correlates to the opposite side, which is our x side. So we want sine 30. And we can plug that into a calculator and get a result for our net force. And so our net force is negative 22.5 newtons. And it's negative as we expected because it points up the ramp. And we expected the block to go up the ramp. And the last thing to point out that we acknowledged before was that F equals ma, where A is just F over m. And so we can go back and look. Our mass was 5 kilograms in the question. And so A is 22.5. And we can go ahead and plug in that negative as well. And we'll end up with a negative acceleration, which just means to the left. And our acceleration is negative 4.5 meters per second squared. And that is the magnitude of the acceleration up the ramp. And so this problem became a little bit simpler when we rearranged our x and y coordinate planes. By choosing an x along the incline, the problem becomes a lot simpler. It could be a little bit tricky to become fluent with sort of how gravity points at an angle instead of pointing straight down. But once you sort of get over that hurdle of understanding where the forces are applied, the problem becomes a lot simpler than if you were forced to maintain that original x and y horizontal vertical sort of rigid frame. It's very beneficial in a class like this to be able to fluidly move around our coordinate plane.